Who's going to be presenting on a brave new world of slicing and dicing Xarray objects.
Great. Thank you, and thank you to the organizers for giving me this opportunity. I'll note at the outset that I'm presenting on the behalf of a group of people. In particular, I want to shout out Benoit Bowie, who could not make it here, but who's the guy who's really done a lot of the work over the last 3-4 years to make this happen. So we're going to talk about slicing and dicing Xarray objects. My name is Deepak Cherian. Today I'm a forward engineer at EarthMover. I've been an Xarray maintainer for a long time, recently been doing Xarray and IceChunk, which we just launched 1.0 today, so it's great. Woo! Yes, come to the Open Science Happy Hour after this if you want to come celebrate with us, or stop by the booth to find out about IceChunk. I have a background as an oceanographer, and most recently I worked at NCAR, which is one of the world's leading climate research labs, for now at least, before it gets destroyed. But when I was there, I just experienced so much pain working with scientific data workflows in the earth sciences that I decided to join EarthMover and do something more about it. I'm going to talk about Xarray. Everyone here know Xarray? Yes, lots of nods. Conceptually, for this talk, what you need to know about Xarray is it provides data structures that wrap arrays with metadata. And it's like a fundamental fact that all your data almost always has metadata with it that describes what the data is. The specific metadata that Xarray tracks are names of dimensions, in coordinate labels. So you have measurements at a point. What are the coordinates of those points? Arbitrary dictionary of attributes. And the big thing now is this new thing called indexes, which is what this talk is about. The reason you want to use Xarray is because it lets you use metadata to express your analytics. So you can say dataset.mean dim equals time instead of axis equals 0. Instantly readable to anyone. You can say things like, hey, give me all the data for 2024 Jan 1st, instead of saying, hey, give me the index 20. And you had to know that the index 20 was that date. You can say, hey, plot, and put longitude on the x-axis, latitude on the y-axis, stuff like that, right? And we even give you high-level primitives, things like group by time.year.mean, for example, gives you yearly averages. A loose definition is Xarray is pandas, but for n dimensions in arrays, right? And a canonical data set for Xarray has historically been these kind of cubes. You have these underlying cubes, and you have more cubes of metadata or squares of metadata that get associated with it. A couple of other concepts useful for this talk are indexing and alignment. And so I'm going to jump over to a little, Jupyter Lab book. Here is a canonical Xarray data set. A data set has data variables. In this case, this is air. I look at my arbitrary attributes, it tells me it's air temperature in degrees Kelvin. It's a 3-dimensional array. Those dimensions are named time, lat, and lon, right? So that's a 3-dimensional array. This is at surface air temperature. Each of those dimensions is associated with 3 coordinates. So latitude, longitude, and time. These are orthogonal axes. And for those axes, you have tick labels. So this is telling me that I have measurements between 15 degree north and 75 degree north in latitude, kind of 200 east to 330 east in longitude, and a bunch of date times. So I think it's 2 years of data. And so here's some magic. I ask for, give me all the observations for that date. Turns out there are 4, because this is a 6-hourly time series. So you get 0z, 6z, and so on. What just happened? You've queried your data with a label, right? Underlying data is an array. And so at some point, we went from label space, 2024-0101, to a bunch of indices, like 5, 6, 7, 8. Something did a translation in there, that's an index. That little index is sitting here. So this is an index, pandas index, we call it, along the time dimension. And that's the structure that gave us that lookup. And it did it really fast. There's also an index along latitude. So you could do things like, hey, give me lat equals 40. This ends up picking out the latitude equals 40 north value, right? So there was another index along latitude that was used to do that lookup. Now we get a scalar. There's no index anymore, but I still have indexes along lon and time. Next little piece of concept is something called alignment. The way to think about alignment is it's asking, anytime you do a thing with 2 Xarray objects, it asks, are these 2 grids compatible? And then we have to worry about how the grid is defined. So here are two little Xarray data arrays. One is shown in red, the other one shown in black. So these are the points at which you have values. You can see these are two little squares, they're a little offset. And so how do you combine these two, right? These are 2x2 arrays. If you use just bare NumPy, you would add them. You could add them, right? You get another 2x2. Xarray, however, understands the coordinate system. It knows that these values are sitting at 0 in x and 1 in y. It knows that this one's sitting at 1 in x and 2 in y. And so it knows that I can't add this black one with the red one because they represent different points in space. And this is very important metadata. And so when you do try to do that, by default, Xarray will do what's called an outer join, or the union of the coordinate systems. And so I gave in 2x2s, and I get out 4x4s, because they don't overlap. And just to be clear, the way you can do that is by inserting a bunch of NAND. So the data get preserved, but because I've gone from 2x2 to 4x4, I need to do something, and what Xarray does is to fill in a bunch of NANDs. So this is alignment. You decide the output coordinate system, you know the input coordinate system, we make them match, and then we do what needs to be done. Right? This includes merging, includes concatenation, includes binary operations, and so on. Those are two things that are enabled by indexes, because indexes define a coordinate system. And so indexes are what enable this. They translate from coordinate label space to array index space, so they're kind of encoding this transformation to a coordinate system. These lookups are generally quite fast, and what's important to know is those transformations can be quite complex, right? I showed you the simplest three-dimensional coordinate system, right? 3 orthogonal vectors. The world is more complex than that. Tessellating a sphere is hard. Here are some very complicated grids that could also do something like that, but it was hard to express in Xarray. Indexes also define a coordinate reference frame, and so as I showed you, this gets you this idea of alignment that gets used anytime you merge or do things with multiple Xarray objects. We always have to look at coordinate systems to make sure we're doing sensible things. So historically, indexes in Xarray are very useful, but also kind of limited because we inherited them from pandas, which is great. It gave us all of these things like float index, a character index, date time, time delta, but pandas is a data frame, right? And so these indexes are one-dimensional. That one-dimensional nature really just means that all you can do is define a coordinate system that is, kind of 3 independent orthogonal vectors. And so you get these like cubes, like your coordinate system is a cube, kind of fundamentally. It's a cube in the way that Xarray understands it, right? And it comes from this one-dimensional limitation. We built a few more complex things, like we can support a multi-index, we can support CF time index. This was built up for non-standard calendars that are common in climate science. But these were all very special cased. Inside Xarray, lots of custom logic. You can't come and build your own, really. Like we had to admit to at that point. This meant we missed out on a lot. We had no way to represent intervals, particularly time intervals, a common problem. Complex geographical grids are everywhere in the earth sciences. So here are 3 examples. On top is a projected grid. That's the HER forecast model grid, right? It's a little projected grid, which is kind of wonky when you look at it in that projection. The second one is a map of sea surface salinity from a ROMS, a regional ocean modeling system. That's off the coast of Texas in the Gulf of Mexico. That grid is locally orthogonal, but you can see it's kind of following the coast, right? So this is a curvilinear grid. The last one down there is one of these spherical coordinate systems called HELPIX. Again, you can see that each cell is kind of wonkily shaped, right? And so you can represent and work with these data sets in Xarray. It's just significantly less magical if you didn't have these indexes that understood that coordinate system, right? And so people do this today, but it's kind of clunky. And I worked with curvilinear grids for a long time. It was just not so great. And so the big news here is we can go from that simple, 1D orthogonal vector coordinate systems to significantly more complex ones with these custom index objects. And thanks to funding from the Chan Zuckerberg Initiative and NASA's open source tools, frameworks, and libraries programs, we can go from this to that. So we got spheres, we got unstructured grids, we got geometries, sparse things. I mean, this is many, many years in the making. Because it was hard. It's like changing fundamental assumptions of a data model is very hard and a lot of thankless work. So good job to Benoit. So now a group of us, 4 of us, have been cranking the last week to build out, show you what's possible, right? And so the takeaway I want you to take away from this talk is that these indexes are ready to be built after many years in development, and I'm going to show you a selection of cool things that you can do with them. This is a website you should be able to open. Please open it and look at it. It is amazing. It all came together in a week, so we were working quite hard. So this is a little gallery. There's a little text up here on the left. Let me bump up font size. On the left are pages that show you demos of what's possible with a bunch of custom indexes. There's a lot of them here. I am going to show you, I think, about 5 of them. But please browse and see what's possible. I'll start with this one. These are floating point ranges. So range is, this should remind you of, let's say, NumPy's A range. So this index is bundled into Xarray. Zoom in one more. How about that? So Xarray indexes range index. You can create it with A range, just like NumPy A range, and they say I'm going from 0 to 1,000 with a spacing of 10 minus 9. How many points is that? That's a trillion. That's trillion. So this is a coordinate that has a trillion points. But the only reason this is working is because under the hood, we don't actually have a trillion values in memory. We just know the transformation, which in this case is a straight line, right? You can create something similar with linspace. Again, this is intended to be like NumPy syntax. And if I materialize that whole thing into memory, it would be 7 terabytes. So clearly, I have not materialized this into memory, right? And if you index it with slices, a slice of a range is another range. I indexed out 490 points, and I preserved my range index. So the kind of coordinate transformation, the very, very simple one, has been preserved on indexing, right? And so you can now work with that kind of coordinate system. Who here knows about the time bounds problem with Xarray? There's a few. Greetings, fellow nerds. I will illustrate this. I'm going to scroll down. There's a little bit of setup to get the data set to where it is, but couple of concepts, right? So this data has data that is averages over intervals of time. And the way in climate science, a standard way to represent these is to use bounds. Here's an illustration. This time bounds variable is saying I have an observation that's the mean between this edge and that edge, and then this edge and that edge. It's about 6-hour intervals, right? I'm going to scroll down a bunch. So this is how a data, say, would be distributed by a data center, right? You have my air temperature, time lat lon. There's a time vector that's one-dimensional. That time vector is kind of like a central value for that observation or simulation, but it really represents an average over these kind of uniform time bounds that are 6 hours wide, right? I'm going to add the CF interval index. This is the only index that has not been released yet, but hopefully we'll get it in soon. So I add this little CF interval index. It knows about time and time bounds. This is the original data set. If I asked it for my data, look what happens. I get lat lon and time. I lost my bounds. I lost very, very important metadata. This is really bad for a data structure that says I will keep your metadata. And this is because Xarray's defaults for propagating those variables are kind of very simple heuristic. It just looks like, hey, I will give you all the variables that are a subset of these dimensions. With the indexed variable, if I pull out air, I get out time bounds too. Because it's like that index is saying this, I need to carry this variable to propagate information about my coordinate system. You have to take this. And so we've added that extension point that lets you do that. So I added this here. It's kind of like a wonky thing, but this is important because it's saying that the index object lets you override Xarray's data model in fairly fundamental ways, right? So it's really changing what you can do. Next one is coordinate reference systems. This little index is very interesting. Again, I'm going to scroll down past a bunch of setup. So again, I have my little air temperature data set, but what I've added this time is a spatial ref variable. This is kind of a standard way of saying this is the coordinate reference system for this particular data set. This wall of text is the standard way of representing all of that information. It's stored in the attributes. But I find this index very fascinating because this is a scalar. It has no dimensions, which means you can't use it for indexing, but it has very important metadata. It tells you what coordinate system that thing is in, right? And so what we do is you can assign a CRS index now. It says this is this CRS. Why do you want to do that? Well, let's assume you had a different one that was a slightly different CRS. Now, these two objects are not the same. They're not in the same coordinate reference frames. You can't meaningfully add them or do anything really combining them without doing a transformation to move them to the same coordinate system. Historically, if you try to add these two data sets, even though they conceptually represented different coordinates, it will let you do that, and that was meaningless. Today, if you do that with CRS index, it will tell you that's a bad idea. Do something else. So it catches these errors. But this is fascinating because, again, it doesn't let you index, but it does let you align. Remember, indexing and alignment, the two things, right? This is a scalar that tells you information about a coordinate system. More cool things. Here's a raster index from Rastrix. This is another example of this coordinate transforms, right? And so a lot of geospatial data comes out with what's called an affine transform. So again, I'm going to scroll past a bunch of setup and say on the spatial ref variable, there's this thing called a geotransform. And these six numbers define what's called an affine transform. So in there is the top left corner, which is an origin. There's also a spacing in X, a spacing in Y. And then the other piece of information you have is the size of the dimension, in this case, 332, 316. So between those six numbers, you can define an analytic coordinate system. It's just linearly spaced points starting at this origin till that end, right? And so you can assign this little raster index. By default, this data only comes with those six numbers to define the coordinate system. It doesn't actually come with coordinate values. But when you assign this index, it creates these fake coordinate variables. They're not realized into memory. We realize three numbers just to show you the repr, but it says there's X and Y with these coordinate values, but again, it's represented by a transformation in the back. It's lazy. This one's extra cool because, again, anytime you slice them out, you can preserve the transformation. So here's a little slice. But anytime I sliced out a bit of my data set, I get raster index back. You can compare the transforms underneath. Notice that the offsets have changed because, again, I've sliced it out, right? So the spacing has not changed. That's 25,000, negative 25,000. But the offset, the origin has changed because I've now sliced out a region. This package I really like, because I wrote this little bit, which is super fun. I take my original data and I slice to 150 and I slide 150 to none. So I've taken out a left half and a right half, right? So the whole coordinate system was going from -4 to 4, -4 to 4, and I've cut it into two halves. I can concatenate them. And what happens when you concatenate that back? You get back to the same place, right? And look, I've created that index back again. And so put it back together, you get this whole thing represented again symbolically, right? And so what it's done is, again, remember, this is the idea of coordinate systems represented as a function, right? It's like the index gets to say, hey, I'm going to combine this one and this one. I can represent that as another one, a new transformation, and I can send myself back. The last one I will highlight is a very cool thing called a vector data cube. An illustration is here. Imagine a three-dimensional cube. One dimension is indexed by integers. The second dimension is indexed by strings. And the third one is indexed by geometries. So that's kind of wild. Here is a data set. It's two-dimensional arrays. One dimensional is county. There's about 3,100 counties in the US, and it's 4-year averages of, I guess, or estimates of population and so on. Along this county dimension, I'm going to use this XVec project, which is very cool. I'm going to say, hey, set these geometry index along that county dimension. And so geometry index actually comes from GeoPandas. So now we're going to pull functionality that's been developed for a whole different paradigm, right? Like data frames, geodata frames. And I'm going to say, hey, we can wrap you because you look like a pandas index. And we know how to do that. And so I'm going to assign a little geometry index along this county dimension. Why do you do that? Because that lets you index with geometries. I can give it in a geometry and will give me the right thing back. So say, hey, give me that county back. Then it comes back. You can do more complex things. With Shapely, I'm going to define a box. So this is just, imagine a little rectangle. I can pass that to standard Xarray API.cell. And I can say, hey, give me select all the counties that intersect with that box. Right? So intersects is not something Xarray does by default. The index knows about it. You do that, you find that there are 63 counties intersecting that box that come back out of those 3,000. Visualize that, that's it. Right, so this is Washington. Isn't that cool? So this is why we are all so excited, right? You've really changed what you can do with like standard Xarray things. And it's really enabled by this really fundamental new object called an index, which is now an explicit part of Xarray's API. Writing this stuff is a little complex, and so our goal here is to make it really easy for you guys to do this. And so what we're trying to do is provide building blocks, right? And so this next one is what's called a coordinate transform index. It tries to abstract away as much as we can so that you have less to build. This is the one that underlies both the range index and the raster index I showed you. The range index is simple linear transformation. The raster index is a little more complicated, but still fairly simple. There's an incomplete example here that tries to build one using an SciPy world coordinate system object, right? So SciPy now has these definitions for functional transform, and like we can plug that into Xarray. This is incomplete. If someone wants to build it, please come to the sprints, and we can finish this. But anyway, this is kind of illustrating the point that we're trying to abstract away as much as we can, and leave it to you to define just very little adapters that will let you plug in your custom domain logic. Last one I'll show off is ND point index. This does nearest neighbors, so things like KD trees. I'll go all the way down to the complex example here. Again, I'm going to pull out this little curvilinear grid, and I'm going to sample a straight line trajectory through it and say, hey, do nearest neighbor sampling. This can be done. I'm running out of time, so I'm going to scroll down, but please look at this website again. I'm going to say ND point index, and I'm going to customize it and say I'm going to use this ball tree metric, not just default KD tree, right? So there's a little adapter again you can throw in. I can do again dot cell this trajectory. This is standard Xarray syntax, method equals nearest, and then boom, here's a straight line output. Right? All done. So indexes kind of extend the classic data model. Even if you have cubes as your coordinate system, now you can do functional coordinates. You can do more complex 1D coordinates like intervals. You can look at more complex cubes. I didn't show you much of this today, but Eustace had a talk earlier about discrete global grid systems. So these are these spheres. Unstructured grids. I showed you vector data cubes and tree-based indexes. So we've really expanded what you could do with this new data model. When do you build an index? Anytime you need to do something with coordinate labels, but more generally, indexes control information. This is how I think of it. So that CRS index, they used like a spatial ref thing, right? It was scalar. It doesn't really help you index things, but it helps you define the coordinate system that Xarray knows about. Importantly, there's a well-defined way that Xarray will use them, so they're a lot more reliable than just dumping metadata attributes in adders. And it works well with kind of our extension API, which we call accessor. So here are a couple of examples of things you do with this XVec project. It adds a little XVec namespace and all kinds of domain-specific logic under there that uses the geometry index. Skip that slide in the interest of time, but it's basically the idea is that indexes are very customizable. People are very excited. Here's a couple of interactions I've had on GitHub in the last week. One on the left is a project called XRadar. One line, solving lots of problems. On the right is this project called XUGrid that tries to represent unstructured grids in Xarray. This has historically been a royal pain, and they've come up with very complicated workarounds, but to quote, basically it seems to work incredibly well so far. I've chucked my wrap module, which was by far the worst part of XUGrid. So this is really fundamentally changing what you can dump in and do nicely with Xarray. So the last slide. Key takeaway is indexes are ready to be built after many years in development. They're pretty sophisticated, but they're also really exciting. And we are here to help. We're working on documentation, and we're explicitly working on providing these little building blocks that you can adapt really easily. And we've built that gallery of examples for inspiration that you can click through and see what else is possible. I've only shown you 5 out of 10 or something. Ian, Eustace, and I will be at the Xarray Sprint on Saturday, so come chat with us if you want to experiment building one of these. And I'll be hanging around the Earthmover booth a bunch. Stop by if you want to chat. Thanks for listening.
All All right, opening up for questions, and we just got one from Axel. Is the coordinate bound scheme only supported for time-like axes or for arbitrary ones?
Arbitrary ones, at the underlying level, we use pandas, basically. So any pandas, anything that can be put in a pandas interval index would have worked there.
I have a question. So you talked about geometry and vector data cubes. Can you elaborate on use cases where you would use that versus your typical GeoPandas for handling vectors?
Yeah, I think the key thing there is the multi-dimensional aspect of it. So if you remember, that cube had one geometry dimension, counting, and the other dimension was time. And then you can imagine even more dimensions, high-dimensional cubes. And so once you hit that many dimensions, a table or a data frame ends up being clunky. And so that's where it really starts to add.
Thank you. Ellie or Eli, I'm sorry, asked, how does this affect, if at all, Xarray integration with Dask for computing on chunked data?
It does not affect it at all because it's more about the coordinate system rather than the underlying arrays that you're computing on.
And then Nick asked, what does the storage of these index functions look like when I save a data array or a data set to netcdf or Xarray?
These indexes, this is a really good question. These indexes are kind of constructed at runtime, and at the moment we don't really serialize anything to disk. And so when you read in, we build it, and then when you write, we don't do anything, so it gets lost, right? So we don't really have a serialization story yet. Could be done.
And then from David, what was the most difficult part for you to implement?
For me, to be clear, I didn't do much of the really crazy refactoring that went into doing this. The bits that I did implement were a couple of indexes. The piece around that raster indexing where I showed you can combine the two back to get back to the original coordinate system. That was pretty hard, but also interesting. So it's kind of deciding that there are these two bounding boxes, that you can stitch them together, and that makes sense and can be represented by another affine transform. It's kind of cool. So I was excited to show it off.
Any other questions? Well, we have a few more minutes. Maybe I'll give it a few more seconds in case anyone wants to ask questions in the Slack. You got through those pretty quickly, though, I gotta say. Okay, well, I think we can wrap it up then. Thank you so much.
Thank you.